Okay, good morning, everyone. Let's see. Before we start today, I want to finish the set of slides called Lecture 6. Still talking about some natural torques, and then we'll switch gears and start looking at the equations with momentum exchange devices. So we'll extend the dynamics models that we've seen so far, adding moving parts inside the spacecraft. Before we start, anyone has questions on the Simonic assignment, homework 1, and the one creating the desired orbit and even gravity gradient? That probably means no. We'll definitely have some time today, next week, to go back also on the gravity gradient that was not finished yesterday. So the simulation, I mean. Okay. So the last words on gravity gradient. We saw last time, yesterday, we saw the damping with a wheel that has a dissipation capability, the steady state as a function of the disturbance torque and the difference in the moments of inertia. So last few comments, if you recall the expressions for C13 and 33, and when we simplify for small angles, we've seen that the torque, I'm sorry, C13 and C23, that the torque about the z-axis, which is for us the yaw axis, it's going to 0 when you have small angles. By the way, this is the LVLH again. When we say small angles, we assume that the body axis will be very close to LVLH, and so that's why I'm interchangeably calling z the yaw axis as z of the body, but obviously there are two different things. But we just know that we have assumed small angles, and so they're pretty much aligned. And so to control that axis, so in other words, to have some action due to gravity gradient about the yaw axis is very difficult. It basically is not almost ever considered, because J1 and 2, the moments of inertia for roll and pitch, they are usually comparable, and all you do when you extract a boom, like we've seen with a tip mass, you usually do it along the z, and so you're going to increase J1 and J1 and J2 pretty much by the same amount. So it's not going to make a difference to deploy a boom in terms of controlling the z-axis. And so the bottom line is that usually with gravity gradient, what you do is control definitely the pitch. That's really the main goal of gravity gradient, and a little bit of the roll, but mostly what you do is the pitch. And if you think about it, that's going back to what I mentioned at the beginning, which is you get some kind of pendulum-like behavior, and really it's the second axis that is the one we usually target with gravity gradient. So, but there are other ways to create damping, and one is exploiting the magnetic field around the Earth. So we can do it in different ways. Some spacecraft have simply a magnetic dipole, the vector D that you see here, that is fixed in the body of the spacecraft. So it's almost like having a magnet on board. And sometimes it can be just a magnet, or coils with current that runs through them at a constant intensity. And so this is obviously only usable when you're relatively low Earth orbit. As you go up, the magnetic field intensity of the Earth, which in this equation is B, vanishes, and you need to have a planet with a magnetic field. Otherwise, it doesn't work. So around Mars, for example, there's almost no magnetic field, so you really can't use this. And so If you want to, for example, detumble a spacecraft deployed around Mars, you have to use some other means, definitely not the standard magnetic moment that we use around the Earth. So, but since we're talking still about gravity gradient in a sense, or at least we're trying to use other means to compensate for the shortcomings of gravity gradient. Well, if you want to stabilize, for example, about the z-axis, you can use a torque like this. So the one axis that is out of luck using gravity gradient can be dealt with using a torque like this. So again, B would be the magnetic field around the Earth, so it changes on your orbit, obviously. There is in the aerospace toolbox in Simulink, there is a block that gives you B as a function of your altitude. I believe it's altitude, longitude, and latitude. I'm not sure if there's more inputs. It's possible, but at least those three. And then the D will be what we control on the spacecraft. As I said, it could be a constant and not something we can vary, but for the most part, it is a vector that we can control in the body axis of the spacecraft, especially if we have three magnetic coils pointing with their axis of symmetry. You can just imagine them as, wire wrapped around some components of the spacecraft. And if their axis of symmetry point around the body axis XYZ of the spacecraft, then you have the capability of creating pretty much any direction for D. So D is definitely given in body frames. B will be known around the planet, and then you obviously in practice, and we're not going to add this to Simulink, at least not for now. And there will be a C body to inertial that projects this B that is expressed in the inertial basis in the body frame. So the question here is, if I have a desired torque, can I solve for D? So compared to what we've seen so far, the other means to stabilize and control orientation a little bit, they were really passive. Gravity gradient is passive. You can, and I'll show you a paper that we just published about the idea, you can in principle go here and think about controlling the torque actively due to gravity gradient by changing, well, you can change N is a given, it's on the orbit. The orientation is what you are trying to change. So you can think about maneuvering a little bit the moments of inertia if you have the ability to change them. So basically you have to change the mass distribution / shape of your spacecraft. But it's very difficult and it's not usually done. Spin stabilization also is not an active, in the classical sense, control mean because you just put something into a spin and you let it go. While here, we can indeed control the intensity and direction in the body axis of the spacecraft of D. So the question is, if I give you a desired torque, and that could be from a control law that we have implemented, can I always solve for D? Well, obviously, by looking at this expression, no. It's pretty obvious that if you, let's see, if you have a B at the specific location where you are, and M, the desired torque, that are parallel, you cannot do it. You cannot really create that torque. If your desired torque is B, is parallel to B, there's nothing you can do really. So, in general, that means that you don't have at least continuous 3-axis control. You definitely have 2-axis control with the magnetic action, but not 3-axis, not in general. You may actually have 3-axis control for the majority of your orbit, but there's always there could be those instants or intervals of time where you require a torque that is very close to B, and so you don't obtain much. So to use this as a way to play and complement gravity gradient, what you could do is that the y-axis, again, the pitch, you stabilize it by gravity gradient. And as I said, that's really the usual assumption that that's the axis I really want to control or stabilize with GG. Instead, the other two, X and Z, you can play with those using these torque rods that are aligned with the Z and X body axis. And so one could propose, if we're dealing with gravity gradient and we want to compensate on the other two axes with this kind of expression, well, you could propose, for example, a solution like this, where you don't activate any coil about the body axis y, the pitch, but you do for roll and yaw. And I have some handwritten notes about what happens if you do so. I'm sorry, they're a little faded. But basically, what do we do here? Mx, y, and z are your desired torques. We know that they are the cross product of B and D. There may be a minus that is missing here. No, it's D, yeah. D cross B, right? So, yeah, I think I'm missing the minus here. Okay. Well, aside from that, we said dy is 0, dz and dx are these proposed torques. If you plug them into this vector, you obtain these expressions for mx, which is mx is equal to mx, so I am obtaining what I want. For my, I get this. So I still get a torque on the y. And then for mz, I do get mz. Okay. So by proposing these three inputs for the, basically this will drive the current that you want to run through the wires. By proposing those three inputs, I do get my desired torque on the x-axis and z-axis, which is what I wanted. But I have this residual, and so to make that go away, you basically just impose this constraint. So you don't have completely independent mx and mz. So it is what it is. It's a pretty cheap torque to get. You only have to run currents through wires. It does require power, but nothing more than that. It's relatively simple to obtain, and so there's a lot of limitations. And in this case, if we want to complement the gravity gradient, we can. It's just that the mx and my, if I want to stick to this proposed control law, and this is just one possible solution, then you may want to consider not allowing mx and mz to do whatever they want. You want to basically include this constraint. So if you're designing a control law, you better design it simple enough that you can also respect a constraint like this. But that's another way. Another approach is if you instead want to really go for three-axis magnetic control, well, one way to do it is, well, you look at B cross, you take the expression that I gave you, M equals D cross B, cross both sides with B, you obtain this expression. Now, if D is perpendicular to B, and that's an approximation we make, we choose to always activate the coils to obtain something like this, then you can solve for D, and this is the equation you get. So this is another possible control law that it's used, but really every time you design a spacecraft, you need to run simulations for anything you want to do with magnetic control. You need to run careful simulations. You need to keep in mind that more than a couple of degrees of accuracy, you can't really get anything better than that. And but you know, it's a way that is relatively simple and cheap to control orientation. Now, I said before when we started the class that for the most part, this type of interaction with the environment is used for detumbling. So the most common use really is either complementing for gravity gradient, as we've seen, or just remove omega, remove any angular velocity after deployment, or bring it down to very small values. So the reality is that nowadays we don't really control orientation with this kind of torque. We mostly just detumble the spacecraft. Okay. All right. we're almost done. We need to cover a few more things in terms of environmental torques. We did talk about gravity gradient. Well, the spin studies, environmental torque. We talked about magnetic torque. We still have not explored what's left, which is the aerodynamic and the solar radiation pressure. Again, these are part of your environment. There's no escape. If you are in Leo, you have the aerodynamic one, and if you are above, the solar radiation pressure can be important. And so, as I said, this should really be part of modeling the dynamics itself. So this is a nice image showing you, still from the textbook from Hughes, that up to about 500 kilometers, the aerodynamic torque is really what dominates the game. In medium height orbits, so say from 500 to GPS altitude, then gravity gradient and magnetic torque are the most important one that you can look at, and then the solar torque prevails above that. Now, it's always to be kept in mind that these are a function of your spacecraft geometry quite often. The aerodynamic one is the solar torque. It's a function of your geometry, how big of a reflective surface you have, or if you have multiple ones, where they are, how reflective they are. Same story for gravity gradient. It really depends on your satellite. So these are the general relationships that tell you that the aerodynamic is definitely stronger in low Earth orbit, but you may have a very long boom, and you can play with things that make gravity gradient as important. So it really depends on your spacecraft, but for the most part, these are the relationships at different altitudes. So how do we deal with the two that are left? Really, the aerodynamic and the SRP, solar radiation pressure. So you can't neglect aerodynamic effects in Leo. The International Space Station is at about 400 kilometers above the surface, and I believe there is a firing adjustment of altitude to regain altitude every couple of weeks or so. Don't quote me on this, but it's not super often, but it requires a boost to regain altitude because there is some atmosphere, and it's a pretty big object. So even if the atmosphere is thin, it's going down. So density is very low in Leo, and the way we end up writing the drag and lift, and forces, and then the torque in terms of formulas, as we will see, it's similar to what you write for an aircraft, just because we are used to aircraft. But the reality is that the model behind those equations is quite different from the continuous flow model that we use in atmosphere. We introduced the kinetic theory of gases, which means that basically you have particles that are impacting with the spacecraft and transfer momentum to the vehicle itself. And really, there's nothing behind the spacecraft, so we don't really model wake or any sort of interaction that is not just things that come to the front of it. Basically, the particles that impact the front, and then they can be reflected in different ways. So we want to definitely find some equations that are usable. So the additional assumptions that usually are made is that these impacts of the particles of the atmosphere with the spacecraft are inelastic, so there's no reflection almost, or the majority, basically the momentum, the linear momentum that they carry, it's completely transferred to the spacecraft surface, and so there's almost nothing in terms of what's left to the particle after it bounces off the surface. And also this means that there is also just a drag component, no lift, no side forces with respect to the velocity, which is not true. There is a little bit of side force, but in first approximation, we can say that it's much less than the drag component. And so this is an assumption that we made over the years for our work in my group, talking about differential drag control, for example. We only say that the interaction with the atmosphere gives you forces on your surfaces that are opposite to the velocity of that surface through the atmosphere. Another assumption is that the mean thermal motion of the atmosphere, it's a lot less than the spacecraft going through the atmosphere. In other words, you can say that the atmosphere is at rest because you're flying very fast through it compared to the mean motion of the particles. Now, this can be removed. There are models for the motion of the atmosphere, and so you can get a little more precise and elaborate in the way you model the velocity of the particles with respect to the spacecraft itself. So you can assume that the atmosphere is rotating with the Earth. It's rigidly attached to the planet. That's the first assumption. And then usually on top of that, you can start talking about models for the atmospheric winds, low Earth orbit. There are models that you can use, and so that gives you a little more realistic representation of the what the particles of the atmosphere are doing with respect to your spacecraft, so they can compose the velocities and get the real direction of drag. For a spinning spacecraft, we also neglect the spinning velocity with respect to the orbital velocity, so it doesn't matter if the spacecraft is spinning or not in these assumptions. So how do we compute the torque? Well, if this ugly potato is my spacecraft, and the circle here is that I'm pointing with my mouse is the center of mass. We look at the infinitesimal surface on the satellite that I call dA, positioned at a location individuated by vector r with respect to center of mass. This velocity dr will be the velocity of the atmosphere with respect to the spacecraft. So the really, it's, since we're doing infinitesimal surface one at a time, we can say that's the relative velocity with respect to the surface, but usually, you know, it's the same for everything because we said that we neglect the spinning motion, and so it's dr for the entire spacecraft. It's the particle spacecraft relative velocity. Then we have this NA, which is a unit vector normal to the infinitesimal surface pointing inside the spacecraft, and then we call cosine of alpha, we call alpha in particular the angle of attack between the surface and the relative velocity, and so it's the dot product of Vr and NA. So the force that is applied to that dA surface due to the transfer of momentum from the particles would be density of the atmosphere, dr squared, cosine of alpha, that in the dA in the direction of Vr. So cosine of alpha dA, as you can see, is the projection perpendicular of the surface dA perpendicular to the velocity, and we call mass flux through that surface, through that projection, multiplied by Vr gives you the momentum flux. It has the dimension of a force. So that this term that you see there, rho Vr cosine of alpha dA, it's has the dimension of a force. Okay, let's see. There may be some dimensionality issue here. Now that I'm thinking about it, I think a square is missing, right? I believe there's a square missing here. Do you agree?
Yes.
Yeah. Because if I look at the two expressions, they have, let's see, in the vector, yeah, that's a square missing here. In fact, in my math type, there was a superscript space available. Okay. All right, so that's the force. If I want to find the force on the entire spacecraft, then I have to perform an integration over the entire outer surface of the spacecraft of that same expression. And in this integral, which is, you know, repeating the same expression I gave you before, this is df, I have this function h of the cosine of the angle of attack, which is a 1 if the cosine of alpha is greater than 0, and it's 0 if it's negative, which means that I'm basically going over the surface and I'm only caring about the front, if you like, of the spacecraft. As I said, there's no wake. This is just impact of particles on the part of the satellite that can see the particles coming in. And so this function is just doing that. It's allowing you to integrate over the entire spacecraft, but only on the side that sees particles coming in. The back doesn't matter. So that's really what this is doing. And along the same lines now, we can compute the aerodynamic torque as a similar integral. H, is still there, and then we have the force on the infinitesimal surface rho of the atmosphere, VR squared cosine of alpha. dA in the direction of VR was the force, and R, we said it's the vector that connects center of mass to any of the portions of surface on the satellite. So this cross product inside the integral is really the aerodynamic torque. And again, we're engineers. We either linearize things or we try to squeeze new formulations into old equations. And this is what I was talking about before, that at the end of the day, we try to write drag force and moments in LEO with expressions that are similar to what you see for aircraft. So for the force, we write that in the end, the drag force, really, that's what it is, rho atmosphere VR squared AP, total projected area, is in the direction of VR, in the direction of relative velocity, is the drag force, and AP is simply the integral of this expression here. It computes the total projected area against the wind. And there is no need for a minus here because the VR is actually the direction of the incoming particles with respect to the spacecraft, so it will point against the motion of the satellite, really, that force. And likewise, we can take the expression that I'm giving here for the aerodynamic torque and write it as a central pressure vector that is crossing the force itself. And so in order to make it work that way, you introduce the expression projected area times CP as this integral. So it's the same integral as the one above, but now there's a vector, there's a disposition vector. So it's almost like computing a center of mass, but the mass are not the weights here. The weights are this H cosine of alpha times cosine of alpha, and in the A, and so it's basically the dimension of a central pressure. That's how we define central pressure. So those are the two expressions that you will find. And so, as I said before, the torque force, the drag force, I'm sorry, yeah, it's very similar to what you would find for an aircraft. Here, the CD doesn't really appear explicitly, but you can make the parallel and say that basically the CD would be AP twice AP, not exactly, but yeah, CD would be, let's see, rho V squared. So you have the 1/2, I think I've ever wrote this, 1/2 CDS is equal to AP. That's really, yeah, that's the parallel you can make. Usually, I think STK, if you're users of Systems Toolkit and many software tools out there, they will give you a default CD for spacecraft that it's of value 2, just because they can, and just because that's been observed over the years. But reality is that if you want to model the CD correctly, then you will have to spend some time before you launch your spacecraft simulating with what are called direct simulation Monte Carlo and other techniques to have a better estimate of what that is, if you really want to write in the end an expression like this, which is usually what we do. Okay, specializing what we've seen for a shape that is not a potato. So say a spacecraft that has flat surfaces, which is a good approximation. You can break down things into flat surfaces, in many cases. So if I have something that looks like this in this image, center of mass is there, center of pressure is somewhere that we need to compute, and so I can go now and focus on each surface independently and then sum them up. Center of pressure of the ith surface is the position of the center of pressure of the surface, which is usually, as you can imagine, the center of that surface, especially if it's a flat symmetric one, minus the position of the center of mass. Okay, so and we're using, of course, the body frame that is parallel to the principal frame with origin on one of the surfaces. So that's why I have this difference vector here, just for convenience. Okay, given the above, the aerodynamic torque that is acting on the genetic I, or 1, I guess this is example for 1, yeah, surface number 1, you know, those expressions that we've seen, they become this one for just one surface, and the cosine of alpha is nothing more than the dot product of the radial velocity and the surface n, because n is just 1 for the surface. There's no curvature, so it's flat, so it's 1 normal, it doesn't change. And then you have this function h of dr dot over n. And then, obviously, for the entire satellite, you will have to sum them up. You have 6 surfaces, so the individual center pressures and forces, and you get an expression like this. Nothing really that surprising, obviously. Okay, let's see. Yeah, that's the same expression. You need to be careful that everything has to be in the body frame. Remember Euler's second law, the equations that we've seen multiple times at this point. Everything there is in the body axis. The angular velocity is in the body axis. The moment of inertia is given in the body axis. So every vector here will have to be in the body axis. So the one thing that needs to, for example, be transformed is the velocity of the atmosphere relative to the spacecraft. If you assume that atmosphere is fixed and the only thing that is really moving is your spacecraft, then in the body axis, in the orbital axis for a circular orbit, your velocity is pointing in the x direction. So you have a vector that kind of looks like this, 1, 0, 0. But your satellite will have some orientation in space, and so you have to apply a rotation matrix that goes from orbital to body. And so that's something to keep in mind. Okay. Concluding remarks on this. What are the big unknown for the aerodynamic torque and force modeling? Well, the CD is definitely one, if we want to write expressions like I've showed you before. But even more than that, it's probably the density of the atmosphere, that raw quantity. There are a lot of models out there that you can find. Simulink and MATLAB come with those if you have the Aerospace Toolbox and block set. The Naval Research Lab model called NRL MCs is one that I think is there. Jackia Bowman models. European Space Agency, I think, developed a DTM 2013. As far as I know, that's the latest one. So there's a lot of models that are functions usually of your position in space, the time of the day, the geomagnetic activity from the planet, the intensity of the sun activity. As you can see in that plot there, you have substantial differences in the density depending on whether you are in the illuminated phase or in the dark. And then depending on the sun activity, you have different behaviors. So you will notice here in this plot that during the day, the density is lower. During the night, in the dark, basically, well, they're just giving you the range of variability. The maximum is during daytime, the minimum is during nighttime. Of course, if the aerodynamic torque is not something you want, you need to also make an effort to design your satellite so the center of mass and center of pressure are as close as possible. And the residual torques have to be compensated for via attitude control. So, since this is work that we do quite often, I wanted to share with you this paper. I uploaded it in your folder just for your knowledge. Just very recently, we published a paper that uses the D3 spacecraft, if you recall, the one with the 4 deployable surfaces, and we combined the drag torque with the gravity gradient torque to control the spacecraft in 3 axes. So without going into the details here, Sani Omar is one of my former PhD students. Camilo just finished in December and is now a postdoc. So this is the system that we are looking at, right? So this is the CubeSat with the 4 deployable surfaces. This is zooming in on the actual 4 deployers in the back. And so what happens for a system like this is that you do get torque, of course, especially if you deploy the booms not all at the same length, but extracting these booms at different lengths also create, as you can imagine, some changes in the moments of inertia, and in turn gravity gradient torques. So in this paper we derived equations to well, we won't go into the details, but we derived equations to try to combine the gravity gradient and the aerodynamic torque to stabilize the spacecraft. So you will see here some results that we can actually obtain 3-axis stabilization. It's really slow. It's not super accurate, but still seems possible. Another paper that I also should upload, maybe, just for your interest, is, let me see, no, this one, not this one. No, maybe yes. Yes. So, talking about the same spacecraft, this is another paper that is basically looking at the CD. Well, it's more than just that, but we definitely have gone through different regimes of light, different speeds, different conditions, and used what was available in literature to give an estimate of the CD for re-entry purposes, but really this could be used beyond just the decay of an orbit. So yeah, I thought it would be interesting for you to see that there's definitely still work done in this field, and that these torques that we're seeing can be used in creative ways, but it really boils down to designing the spacecraft in a certain way. In the first paper I showed you, that means having the ability to change the shape and geometry of the satellite. So, okay, the last one. And then I promise we'll move to momentum exchange devices again. I think we've seen enough equations for all these different torques that now we're in good shape to derive those longer expressions. So the sun electromagnetic radiation does produce a surface pressure, on your surface that intercepts that radiation. It's called radiation pressure or solar radiation pressure. And so it's very similar in the way we model it to drag. It's almost like particles hitting an object. So the effect of the solar wind in general can be neglected, but it really depends on for how long, because if these tiny torques are there for a long period of time, then they do have an effect on you. What are the assumptions? Is that similarly to what we've seen for the drag force, or rather the atmospheric forces, everything is absorbed, so a perfectly black object, so there's no momentum that is left after the absorption, all goes to the spacecraft. During eclipse phase, we just say that there is no effect at all, and also there's radiation that is also emitted by the planet, but we just say that that's negligible compared to the one coming from the sun. Well, some historical references about who discovered this effect, and the math behind it's pretty much the same. Same scenario. Now, instead of relative velocity, you have the direction of light coming to the spacecraft. We talk about electromagnetic flux vector, speed of light, to model P, the force on the infinitesimal surface, or rather safe surface, so we skip it a few steps here, is P, AP, direction of the light. AP is the projected area, like we did before, and similarly we introduced the concept of center of pressure with this integral, which is an average, weighted average, basically, of the position vector, where the weight is this ugly expression here, h cosine of alpha times cosine of alpha. So for a general body, the solar and aero center pressure, they are the same only if, you see, in the particular case of solar vector parallel to the relative velocity vector, as you can imagine. So it's because these integrals are a function of this alpha s angle, and so in general they're not the same. Nothing new here, same kind of scenario to compute the torque. So you basically work very similarly with both. Okay, I think this wraps up what I wanted to give you for the environmental torques. Any questions?
Sorry, Professor, I have a curiosity. Did you also model the shock wave in your paper? Because it seems it looks that you did the paper you have just shown.
Yes.
Okay.
Yep.
And we have not considered it
No.
in the presentation.
No. Well, so if you go back, I would say that no, I didn't mention it, but I'm just wondering if in this representation you can assume almost anything. Well, you could assume that you're considering it. You could actually, because the density is, if the shock wave as it is in front of you, then whatever happens after that is giving you the density, and it will be changed because of the shock wave. So you could follow the same expressions, just keeping in mind that the density of the atmosphere is not the same as in the unperturbed case, that there is a shock wave that changes that before the particles hit your spacecraft. Does it make sense? So does that answer your question?
Yeah. No, just because as I understood in your paper, since you have this square-shaped CubeSat, the shock wave is attached to the probably to the spacecraft. instead, if we consider a potato, we could have a detached shock wave. And I was wondering if how does it affect
yeah, I would say that it makes things definitely more complicated. If you have an attached one or even a detached one, then the density, I would say that the first thought would be that the density of the atmosphere after the shock or shocks, because you may have multiple ones, that you use to formulate the problem, like in this slide, is not going to be just the same raw everywhere. It's going to be different values depending on the location around the spacecraft. Yeah. So that would definitely make it more difficult. But so these are the developments, but the reality is that in practice, this is what we want to write. This is what people write for the drag force and then, of course, for the torque as a consequence. And what we try to do is, well, the velocity is what it is. It's the velocity of the spacecraft through the atmosphere. And then rho, we want to keep that being the atmosphere at rest value, so it's the environmental density, and then all the things that we talked about that we need to model will be captured by the CD. So even the shock waves, like in the paper, you try to make this expression work by working on the CD, and it is so complex and spacecraft specific, as you pointed out, depending on the shape, attached versus detached shocks, that majority of people just say CD is 2, and they go with that. And that comes just from observations of satellites. It's been used for decades now as the reference value. But of course, it's a pretty brute force approximation, really. Not that great. But yeah.
Okay, thank you.
Yeah. Definitely not specifically, as you can imagine, our field of study. This was there's people, usually not in aerospace engineering departments, that deal with these type of problems. This was a visiting student, Simone Raffano, coming from Milano, was in our group for a few months during his master's thesis, and we ended up publishing a couple papers. Yeah, that was quite interesting. Any other questions? Okay. Let's, is the gentleman who was working on gravity gradient modeling here? I don't think so. Okay. Actually, I want to open a slide. Where is it? Here. Okay. So we go back to this. Okay. We have the inertial reference frame, the body one, and we have what we call momentum exchange devices, systems that can change angular momentum inside the spacecraft, and a basis attached to them. So we want to finally derive the equations of motion, like we've done for all those other torques, when we have a system like this on board. And a refresher, J is the matrix of inertia of the spacecraft, just by itself, with respect to its principal axis. Yj would be the matrix of inertia of the assembly or variable speed contra moment gyro in its own principal axis. Gamma j is the gimbal angle, is the rotation of the assembly, this entire system about the g axis. Capital omega j is the wheel spin rate. about the s-axis, and ISJW will be the genetic wheel moment of inertia about, again, the s-axis, the spin axis. Okay. Having said that, how do we find the equations? Okay. You see my piece of paper. So, well, you start from, well, first of all, we remember that Euler's law. I need to be able to see my screen here. Euler's second law tells us that the rate of change of the angular momentum of the spacecraft computed with respect to the center of mass performed with respect to the body plus the angular velocity of the spacecraft or body with respect to inertial observer crossed with hc itself is equal to all the external moments. And remember, this is coming from the transport theorem. It's just that we're able to write to express omega in the body axis of the satellite, which is a non-inertial one, and we're also able to say that hc is j applied to omega bn, where this is again in body axis and this is the tensor of inertia or matrix of inertia or dyadic of inertia that is more easily expressed in the body axis because it becomes a constant. Okay, so regardless of having or not external moments, we need to write this for a spacecraft that has those objects inside that can change angular momentum. So that's why we call them exchange devices. Okay, so for the spacecraft with all those components inside, hc will be equal to j plus, say that we have a genetic number of those, n. So I'm going to write summation I that goes from 1 to n just the first time, and then just summation, assuming that we know it's some number of momentum exchange devices, of the these are the matrices of inertia or tensor of inertia of the genetic J assembly. Sorry, this is J or I or J, doesn't matter. This is applied to the angular velocity of the satellite. I'm going to write these superscripts just this time and then drop them. That's the only omega really. Plus, well, there is one term that looks like this. J goes from 1 to n, and we have y, g, j, gamma j dot about the j axis. This is the contribution to the angular momentum due to the fact that the gimbal can move. Okay, and so it's a contribution along the g axis, and to write basically what I'm doing is I'm writing something like this specialized just to that particular motion. And so you have the moment of inertia, not the matrix, it's just a moment now about that particular axis. Again, keep in mind that these J and these Y matrices are in the respective principal axis, so the matrices are diagonal. And then we have, what else? Well, one last term, which is summation from 1 to n of the contribution to the angular momentum of the wheel itself. So this is Sj. So a term that is similar to this is a time derivative of an angle. So this is definitely an angular velocity, and this is just expressed as an angular velocity. Okay, so this would be kind of in tensor form. If I want to really project everything on the body axis, let's see what I get. I get that H C in body axis. All right, so no more tensors. I'm going to drop the underscores for vectors, tensors, etc. I hope that we know what things are matrices and what things are vectors from now on. Let me know if that's confusing, but we have defined all the variables, so we should know which ones are matrices and which ones are vectors and which ones are scalars. Just because otherwise what I'm going to do next is going to be a pain if I keep underlining things. So, okay. So now, as I said, this is already in the principal axis of inertia of the spacecraft, but the yj's are not. They are in the principal axis of the assemblies, and so I have to move, I guess, project that matrix into a new basis, and so this term becomes summation. Again, I'm dropping the j1 to n as well of Cj yj Cj transpose multiplies the angular velocity. These, okay, let me finish writing this expression and then we'll see what they are. Plus, we have summation ygj gamma j dot, and then I have Cj 100, and then I have summation I S J W omega j Cj 010. Okay, so Cj is the DCM from the genetic jth momentum exchange device to the spacecraft, or what we call B. Okay, so the vector 100 is the vector gimbal axis projected into the coordinate system that is attached to the momentum exchange device. The vector 010 is the spin axis of the wheel in the same as I'm sorry, GST basis. And so this is now projecting everything in the reference that is the spacecraft. Okay. Now, things to say about Cj are that Cj is a function of time and it depends also on the mounting of this system. Of the jth MED inside the spacecraft. Okay, let's let's see what they look like. So for example, the tangential J AT axis as a function of time by V of the gimbal angle, if you want, is a cosine of gamma J A T J is sometimes 0 minus sine of gamma J A S J 0. The law instead that governs S is cosine of gamma J A S J 0 plus sine of gamma J A T J 0. And finally, the G axis actually doesn't change with time. I rotate about that through the gimbal angle. Are these expressions clear? So if you go back to my slides and look at this image here to the right, you rotate through an angle gamma about G. Imagine that you freeze some initial position for S and T, then you know the genetic position for ASJ and ATJ, they will be moving in the same plane of the AS and AT at time 0, and their orientation will be represented just by the angle gamma. And so as you're rotating about G, also the direction of G doesn't change. It's the fixed axis of rotation. Okay. And so going back here, given this, what is my CJ? CJ, by definition, will be B1, B2, B3. So this is dotted with AG, J, AG, J, AG, J, and then you will have B1, B2, B3. These are now dotted with ASJ, 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 and finally B1, B2, B3, ATJ, TJ, and TJ. That's the definition of direction cosine matrix. And for convenience, from now on, we're going to call the first column, the first column just GJ. Then I'm going to call this SJ, and I'm going to call this TJ. Okay. It should be starting to make sense also that this gamma J will be, in a sense, one of my control variables. That's something I will actuate on, and so that's why I'm not expressing it as a function of time, because that will be assigned by some control law eventually. Okay. Do you all want to take a break? 2 minutes?
Yes, maybe it's better.
Yeah, so then we start with some interesting calculations. Let's resume at the 10-minute mark, okay?
Okay.
Okay.